covering a couple of different answers from different sources. What is a quantum computer? This will be, 5 to 7 minute videos, just trying to cover some level topics and answers from different places. So, according to Wikipedia, quantum computing, which I searched for quantum computers, so that's kind of weird, but quantum computing is the exploitation of collective properties of quantum states, such as superposition, entanglement, and to perform a computation. The devices that perform quantum computations are known as quantum computers. They're believed to be able to solve certain computational problems such as integer factorization, which underlines the RSA encryption, substantially faster than classical computers. The study of quantum computing is a subfield of quantum information science. Expansion is expected in the next few years as the field shifts towards real use application in pharmaceutical, data security, and other applications. Quantum computing began in 1980 when a physicist, Paul Benioff, proposed a quantum mechanical model of the Turing machine. Fancy. Richard Feynman and Yuri Manin, I apologize if I butcher those names, later suggested that a quantum computer had the potential to simulate things a classical computer could not do feasibly. In 1994, Peter Shor developed a quantum algorithm for factoring integers with potentially to decrypt RSA encrypted communications. Despite ongoing experimental progress in the late 1990s, most researchers believe that the fault-tolerant quantum computing is still a rather distant dream. In recent years, investment in quantum computing research has increased in the public sector and private sectors. On 23rd October 2019, Google AI, in partnership with the NASA, claimed to have performed a quantum computation that is infeasible on any classical computer. And then IBM was like, no you didn't, we did it with a supercomputer. So IBM actually was like, you didn't achieve quantum supremacy yet. There are several types of quantum computers known as quantum computing systems, including the quantum circuit model, quantum Turing machine, abatic quantum computer, one-way quantum computer, quantum cellular automata, and most widely used is a quantum circuit. I think that's what IBM uses, is the quantum circuit, which based on the quantum bit or qubit, which is just analogous to the bit classical computation. A qubit can be a 1 or a 0 quantum state, or in a superposition of 1s and 0 states. When it is measured, however, it will always be 1 or 0. The probability of either outcome depends on the qubit's quantum state immediately prior to measurement. Efforts towards building a physical quantum computer focus on technologies such as transmons, ion traps, topological quantum computers, which aim to create high-quality qubits. These qubits were designed differently depending on the full quantum computer's computing model. Whether quantum logic gates, quantum annealing, or abatic quantum computation, there are currently a number of significant obstacles in creating useful quantum computers. It is particularly difficult to maintain qubits in quantum states as they suffer from quantum decoherence and state fidelity. Quantum computers therefore require error correction. Let's see. So this kind of goes over a quantum circuit, what that looks like, and the prevailing model of quantum computation describes the computation in terms of a network of quantum logic gates. This model has been thought of as an abstract linear algebraic generalized of a classical circuit. Since the circuit model obeys quantum mechanics, A quantum computer capable of efficiently running these circuits is believed to be physically realizable. Memory consists of n bits of information, has 2 to the n possible states. A vector representing all memory states thus has 2 to the n entries, 1 for each state. This vector is viewed as a probability vector and represents the fact that the memory is to be found in a particular state. In the classical view, one entry would have a 1 of 100% probability of being in this state. All the other entries would be 0. In quantum mechanics, probability vectors are generalized to density operators. This is typically a rigorous mathematical foundation for quantum gates, but the intermediate quantum sector vector formalization is usually introduced first because it's conceptually simpler. This article focuses on the quantum state sector formalizing for its simplicity. Oof. This is really high level stuff. I'm barely grasping any of it. We begin with considering a simple memory consists of only 1 bit. If this memory may be found in one of 2 states, the 0 state or the 1 state, we may represent the state of this memory using the dyadic notation so that okay, so this is like some weird bracket notation, and 0 and then a bracket and then equal 1 over 0. I don't know how to read this. It's kind of hard. It's a lot of math, which a lot of these math symbols I've never learned, so I'll probably have to look all these up. And I think as abstraction goes, the more people we get behind actually learning quantum computers and things like that, the easier it'll be to abstract a lot of this math stuff, because even in the beginning of like classical computing, people actually did most of that stuff in their heads, and so now we have like high level languages like Python and JavaScript or React and things like that like you don't have to know binary to program anymore. So I feel like it's gonna quantum computers are gonna do the same thing here. I am pretty much out of time. I try and keep these videos to like 7 minutes, so definitely do some further research, keep studying, and you will become the next Hokage. So this has been Jeremy trying to teach what I'm learning, which is quantum computing. There's a bunch of different applications for it, a bunch of different terms and keywords and things like that in this process, so keep at it, and